Okay, this is chapter 3. It's entitled Transforming Functions. And before you go through this PowerPoint, it would be wise if you carefully review the Graph Tech Lab and the beautiful compositions. So really go through those carefully and make sure you have a good handle on what is being explained in those documents. They're really good activities. You can couple that with playing around with either your graphing calculator and seeing some patterns, or even with GeoGebra, which is how I make a lot of my graphs, and it's an activity that you'll be doing for the problem set as well. So please go back, make sure that you have a good handle on that stuff. And this little box here to the left is an example of a horizontal shift, and it's one of the many transformations that we're going to be studying in this chapter. So let's go on to the first slide. So although our textbook identifies 7 parent functions, there are actually, more than those. It depends on who you talk to and what they include in their list. So here's the list that I've put together, and I've indicated in red what's not included in our chapter or what's called something different. So notice that although there's no linear function per se, our textbook is always comparing other functions to a linear function, so they kind of technically are including linear functions. Our textbook also includes sine, so this sine function that I'm mentioning right here is only one of 6 different trig functions, and so I'll talk about those in the next slide. But for right now, these are the functions that we're going to be working with. Sometimes they're called different names. Log gets handled separately in another chapter, but other than that, these are important functions for you to know. Okay, here is the slide I just alluded to. It lists all the trig functions. So I know it's a little bit hard to read it, but this is sine, cosine, tan, and then the reciprocal of sine is cosecant, the reciprocal of cosine is secant, and the reciprocal of tan is cotan. So this is what each of those functions look like. Okay, and you can see that they are cyclical. They're periodic is another phrase for that. They have a certain pattern that repeats over and over again. In terms of functions that occur naturally in life, a lot of those will be sine and cosine functions, population fluctuations, the tide, the cycles of the moon, all of those can be modeled using sine and cosine. So this is a very important class of functions. We're not going to be doing a whole lot with them in this chapter, but know that they are an important class of functions that you certainly will study going forward. Okay, here in 3.1 is where they start their discussion about transformations, and transformations are an integral part of any study of functions. So you have a parent function, and then that can be changed by various transformations, all of which are summarized right here for us. And as I said, the Graph Tech Lab is going to assist you greatly in your understanding of transformations, as will our second problem set. There's also a great site that's right here. It's called Math is Fun. You can use that site also to practice doing some transformations and start recognizing some patterns. Okay, so here's the list, but it's really better if you can play around with your functions, go through the Graph Tech Lab, go through the compositions or beautiful compositions handout. That's a good one as well. And just utilize your graphing calculator. Graphing calculators are wonderful for being able to see patterns quickly. You don't have to graph everything by hand. You can see a pattern a lot quicker using your graphing calculator. So go ahead and start to own these transformations. Okay, the beautiful compositions document that's posted on the portal or on Joule will certainly help you with compositions. They're also called sequential relationships. So how to read compositions, this is from page 110. So if you have this expression, you read it by saying f of g of 10. And what happens is you work from the inside out. So first, you're going to do g of 10. You'll get a value for that. You're going to put that value, your g of 10 value, into the variable that's in the f function. That's how you create a composition. Okay, let's go on to the next slide. Okay, in this slide we present a little bit more about notation for compositions. This little circle right here indicates a chain of functions. So you say f of g, and this is equivalent to this notation. Be able to recognize and respond to both kinds of notation. Okay, when functions g and then f are performed in sequence, so remember g comes first, do this first. The result f of g of x is called the composition of f with g. Okay, so this notation is important and is denoted by the symbol f of g. The symbol indicates that g is performed first. Okay, this is performed first. So let's just quickly do one. What if we have f of x equals 7x and g of x equals x minus 3? Okay, if I'm going to do f of g of x, that notation is equivalent to f o g of x. What I'm going to do is I'm going to take this f function and put inside it the g of x function. So I'm putting this in first, and I'm replacing what was the original f of x function. What if I want to do g of f of x? How does that work? Well, that is g o f x, and in this situation what I'm going to do is I'm going to take that g of x function and I'm going to put in the f of x wherever I have an x. So g of x becomes 7x minus 3. Okay, so you get two very different functions, whether you do FOG or GOF. Okay, here's a second opportunity to practice doing compositions. So consider these two functions a little bit more complicated than my previous example. Here's our f of x, and here is our g of x. So if you're going to form FOG, we use the output of g as an input to f. So here's your input to your f. Okay, so your f initially was x squared. It becomes this input squared. Then I had plus 5x. Well, now it's plus 5 times this input, and then continue your function minus 1. Okay, let me change colors. And can you do g of f? So that means that you take the f function, and wherever you find an x in the g of x function, you're going to replace it with that f function. So therefore, g of f is going to equal 1 over, I could write x, but instead I'm writing f of x, which is this, and then plus 2. Okay, so you would simplify this before you presented it as your final answer, and negative 1 plus 2 ends up being positive 1. So that would be how you would present your final answer for g of f. Okay, when you are doing your compositions, you have to be careful. So for any two functions p and q, the domain of the composition of POQ is subject to two constraints, not just one constraint. Okay, since Q goes to work on the input first, any input X has to belong to the domain of Q. Okay, so for example, if Q was 1 over X, then X could not be equal to 0. Do you see that? So you would have to eliminate 0 from your domain. Then let's go on. Since P processes Q of X, all values of q of x must be acceptable to p. That is, they have to belong to p's domain. So what if p equaled radical x? That would mean that you could not put any values here that would be negative. So no negative values. So that's going to be a secondary constraint on your domain. So be careful when you're creating compositions because there are some implied domain restrictions that do not go away. They get carried through the composition. Okay, in section 3 of chapter 3, they talk about inverse relationships. So inverse relationships, simply put, are functions which, or inverses are functions which undo other functions. So with composition, so your FOG and GOF, we can check if two functions P and Q are inverses. Okay, so if P and Q are inverses, something special happens. So when you do P of Q, you'll get the same answer as when you do Q of P, and that answer will be X. So you have to have all these things happen at the same time. If that is the case, then P and Q are inverse functions. Okay, so if the ordered pair AB, so let's say they give you a table, if you notice that every ordered pair AB that belongs to P, and you notice that for Q, you have the BA pairs, then that's another way to check for inverses. For example, if you have, we'll make them X and Y's. If we have 1, 2, 3, 4 for P, and then for Q, if they were inverses, what we would expect to see is 2, 1, and 4, 3. Okay? All right, if P and Q are inverse functions, then the slope of P times the slope of Q will equal 1. So for example, if the slope of P, it's a line, say, was 2, then the slope of Q would be 1/2. If the slope of P was 3/4, then the slope of Q would be 4/3. If the slope of P was negative 5/6, then the slope of Q would be negative 6/5. Okay, get the hang of it? Okay, let's go on to the next slide. Okay, this slide has a little bit more about inverses. For one, we can say the inverse of P, or this is the appropriate notation, P to the -1 power. All right, that's the notation for inverses, and you want to be able to recognize this. Okay, so how do we make an inverse? So if you have one function, how can you get its inverse? So I tried to color code this for us. Okay, if this is the original function right here, then what we know, that's in function notation because it says f of x equals. It doesn't say y equals. So change your function out of function notation and put it in y equals notation. So that's what I'm doing right here in this first step. Okay, next, after you take it in out of function notation and put it into y equals notation, we're going to work towards getting the inverse. So to do that, you're going to next switch your x and your y. So just physically switch them. Wherever you have an x, make it a y. Wherever you have a y, make it an x. Okay, so that's the next step. And then now you're going to solve for your new y. Okay, so you're probably going to have to isolate your y. So when I isolate my y, I get this for my new y. That's the inverse. So once we've done that, then the next thing you want to do is to return to your inverse notation. And so since you had f of x for the original function, the inverse is f -1 of x. Okay, so you want to know how to get an inverse given the original function. Okay, there is a certain geometry of a function and its inverse that's important to note. Okay, you can reflect the graph of f of x in the line y equals x to get the graph of f to the negative 1 of x, which is the inverse. Okay, so which lines are which here? Okay, so the graph of f of x, if f of x was 7x minus 4, I believe it is, that's your green graph. Okay, so that's our green. This is this, and that is your original function. Okay, so next we have to have the line y equals x. So that line is here, it's the red, and that was this. Okay, so then what's our inverse function? Well, if you reflect the green line over that red line, you will get the blue line, which is your inverse, and this is its equation. Okay, but graphically, I didn't have to have an equation. As long as I had a graph of my original function, if I simply reflect it over the line y equals x, I will get a graphical representation of the function. That happens to be the inverse. Okay, when one speaks about inverses, it is perfectly natural to talk about vertical line tests, horizontal line tests, and one-to-one functions. Okay, a relation or a relationship, depending on how you speak about relations in algebra, a relation is a function if it passes the vertical line test. So for example, a parabola is a function because if I draw a vertical line, I only hit that function one place. Okay, so that makes a parabola a function, the vertical line test. Okay, a function has an inverse that is a function if that first function passes the horizontal line test. So you can readily see that this parabola is not going to pass the horizontal line test. What will pass the horizontal line test? Well, let's think about our other functions. How about if we do the square root function? Will that pass the horizontal line test? The answer is yes. So that function must have an inverse that's a function. Okay, if a function passes both the vertical line test and the horizontal line test, it is called a one-to-one function. And if a function passes both of these tests, you can then reflect the function in the line y equals x to find the graph of the inverse function. Okay, so you want to think about this slide, go over the terminology, know what a vertical line test is, know what a horizontal line test is, and know what a one-to-one function is. Okay, the last topic covered in this chapter 3 is symmetry. So symmetry in functions. So there's two kinds of symmetry that they talk about. One is even symmetry. If you have an even symmetry situation, what's going to happen is you're going to have symmetry about the y-axis. So that means the left side of the function is a mirror image of the right side of the function. So this is similar to, say, in the human, your spine. Okay, we demonstrate even symmetry. So the right side of your body is a mirror image of the left side. The parabola has even symmetry. Algebraically, the way you determine that is if you were to put a negative x, so let's say a negative 1, in the function, you would get the same y value if you put a positive x or positive 1 in the function. They both give you the same y value. That is an even function. Okay, in the next slide, we're going to talk about odd functions. Okay, so the opposite of even is odd. And odd symmetry results when you think about rotations around the origin. So it's symmetry about the origin, and the origin is the point 0, 0, is termed odd symmetry. Okay, so if you rotate this figure 180 degrees, it'll return the exact same graph. That is odd symmetry. So graphically it looks like this. You can just picture rotating this 180 degrees and getting the same picture back. Algebraically, this is the relationship. So if I take, so let's say that we're going to use 1. So the f of negative 1, so x is 1, negative 1, that y value is negative 1. Okay, if I put in a negative 1, I get out a negative 1. If I put in a 1, I get out a 1. So those are related by taking the negative of it. Okay, so this is odd symmetry. Do you remember what the even symmetry looks like algebraically? F of negative x would equal f of x. Do you see the difference? This is even symmetry. Okay, you want to understand the difference between these two. Okay, that ends our video of the notes, but there are very many more documents for this section that are probably more important than these notes. So make sure that you study everything that's posted so that you will have a good understanding of functions, of transformations of functions, of compositions of functions, and all that goes in this chapter.